So in my previous class, I started discussing the solutions for the questions in the assignment in center of mass and conservation of linear momentum. I have already discussed the solutions of the questions numbering from 1 to 10. Next, I am going to discuss the solutions of the questions numbering from 11th onwards. Come on, look at the question number 11 on the screen. This question was given one of the All India medical entrance exam papers also. So the question number 11. Two blocks of masses 10 kg and 30 kg are placed along a vertical line. The first block of mass 10 kg at the top is raised through a height of 7 centimeter. The distance that should be moved by second mass to rise the center of mass by 1 centimeter is. So here I choose the vertically upward direction as the positive direction of x-axis, positive direction of y-axis. So I choose the vertical upward direction as positive direction of y-axis. Suppose I choose some fixed point on the ground as the origin of the coordinate system. The mass of the first body we denoted by m1 equal 10 kg, m2 equal 30 kg. If y1 is the height of the first mass above the origin O, in the first case y2 is the height of second mass, then vertical height of center of mass above the point O. In the first case we can write m1 y1 plus m2 y2 by m1 plus m2. So in the vertical height of center of mass above the origin O, in second case I denote by ycm dash equal m1 y1 dash plus m2 y2 dash by m1 plus m2. If you subtract the first equation from second equation, so come on, you simplify it yourself. So you get delta y for second mass, m2 will get minus 1 centimeter. Delta y2 or delta y for second mass is minus 1 centimeter. You simplify it yourself. In case you need time, you can take a pause and copy down the solution and complete the simplification yourself. So you get delta y equal 1 centimeter for second mass. That means what? Second mass must be moved downwards by 1 centimeter. In case you need more time to copy the solution of the problem, you can take a pause and take your own time. So for question number 11, which I have discussed just now, second option is answer, 1 centimeter downwards. Next, look at the, for question number 11, second option is answer. Look at the next question, that is the question number 12. From a circular disc of radius 52.8 centimeter, a square is cut out with a radius as its diagonal. The distance of center of mass remainder from center of the disc is. So I denote the radius of the original circular disc by capital R, which is equal to 58.8 centimeters. In the past, I have discussed a similar case. One of special cases similar to this problem. You have to find the ratio of the mass of the square piece which is cut out and the mass of the remaining circular disc. So I am drawing circular disc in roughly here. This is a circular disc. I denote the radius of the circular disc by Kepler. Let C denote center of mass of the original disk before the square piece is cut out. Now a square piece is cut out from it. Let M1 be the mass of the remaining plate. Let M2 be the mass of this square piece which is cut out. C2 be the center of mass of the square piece, which will be at center of square piece. That means at a distance R by 2, the diagonal square piece coincides with the radius of the one of the radii, with the radius of the circular disc. The length of the diagonal square piece cut out is equal to radius of the circular disc. Let C1 be center of mass of the remaining disc with mass M1. C2 be center of mass of the square piece cut out, and M2 is the mass of the square piece which is cut out. That means C2 is center of mass of M2, C1 is center of mass of M1. Suppose if the square piece which is cut out from original disk is again put back in the original position, then the center of mass of the system will be at C. It means center of mass system of the two masses M1 and M2 will be at C. C will lies in between C1 and C2. That means C1 lies to the left side of C. Let D1 be the distance between C1 and C, and D2 is the distance between C2 and C. Here D2 equal R by 2. The system of two bodies of mass M1 and M2, you can write D1 by D2 equal M2 by M1. So I have to find the ratio of M2 by M1. So total mass of M1 and M2, that means M1 plus M2 is the mass of the original disk divided by mass of the square piece which is cut out. That is equal to ratio of the area of the original circular disk divided by area of the circular piece. Area of the square piece which is cut out from the original circular disk. Here it is the area of the original disk. Because uniform disk density and thickness will be same. Mass can be written as volume into density. Volume can be written as face area into thickness. So if T is the thickness of the disk and rho is the density of the material of the disk, total mass M1 plus M2 can write AT rho. M2 can be A2 into T rho. Thickness T and density rho are same throughout the disk. Area of the original circular disk is equal to pi into Kepler square. Area of the square piece which is cut out is equal to half of the square of the side of each edge of the square piece. Let small a denote the length of each edge of the square piece. So length of the diagonal of the square piece is equal to root 2 times its length of each edge. That is equal to R here. So A can be written as R by root 2. Or you can write R by A equal to root 2. So on the left side you can write M1 by M2 plus M2 by M2. So M1 by M2 on the left side we'll write it as it is. M2 by M2 can be written as 1. So pi into R by A whole square. We can substitute R by A equal to root 2. So M1 by M2, you get 2 pi minus 1. Ratio of the distances D1 and D2 of the two masses M1 and M2 from center of mass of system of the two masses is equal to inverse ratio of their masses. So you can write D1 equal to D2 into M2 by M1. Here D2 means distance between C2 and C, that is equal to R by 2. M2 by M1. M1 by M2 is 2 pi minus 1. So M2 by M1 you can write 1 by 2 pi minus 1. Now you can substitute the given values. So R is given as 52.8 centimeters. You can substitute pi equal to 3.14 into 2 here. 2 pi means. Come on, copy down and complete the simplification part yourself. If you need time to copy these notes, if you want to copy the solution of this problem, then take a pause and copy down the solution of the problem. Come on, complete the simplification part yourself. So you are get the answer as 5 centimeters. So fourth option is the answer for question number 12. Now next see the next question, question number 13. Consider a two-particle system with the particles having masses m1 and m2. The first particle is pushed toward the center of mass through a distance d. By what distance should the second particle be moved to keep the center of mass at the same position? This I have discussed in one of the special cases actually, but still I would like to discuss the calculation for this. Here center of mass system of the two particles is at the same position in both the cases. Therefore distance of center of mass from a fixed point to remains same in both the cases. Let what be the origin of the coordinate system which we choose it to some fixed point. Let x1 be the initial distance of m1 from the origin. Let x2 be the initial distance of m2 from the origin. Let C denote the position of center of mass as the system of the two masses, which remains at same position. Let x1 dash be the new distance of m1 from the origin. Here it is given that the first mass m1 is moved by distance d towards second mass m2. Let us have a second mass m2 is moved by distance d dash. Or we can in general we denote distance moved by the first mass from its initial position by s1, distance moved by second mass from its initial position by s2. But center of mass is at the same distance from the origin in both the cases. Let x2 dash denote the new distance of m2 from origin. Similar calculation I have already discussed in the special cases which I discussed earlier, but still I am discussing again. XCM equal XCM dash, because center of mass is at the same position both the cases. XCM in the first case you can write m1 x1 plus m2 x2 by m1 plus m2. XCM dash you can write m1 x1 dash plus m2 x2 dash by m1 plus m2. So you can write m1 into x1 dash minus x1 equal to m2 into x2 minus x2 dash. m1 into x1 dash minus x1 equal to m2 into x2 minus x2 dash. x1 dash minus x1 gives you the distance s1 moved by the mass m1. x2 minus x2 dash gives you the distance s2 moved by second mass m2. So s2 you can write m1 s1 by m2. Here s1 is given to be d. So s2 will be m2 d m1 d by m2 d. So s2 will be m1 d by m2. If you want to copy the working, you can take a pause and copy the working. So for question number 13, you get the first option as the answer. Next, I am going to discuss the next question. That is the question number 14 here. Two objects of masses 200 gram and 500 gram possess velocities 10 I cap and 3 I cap plus 5 j cap meter per second respectively. The velocity of the center of mass in meter per second is. So the velocity center of mass system of 2 point masses m1 and m2 given by Vcm bar equal to m1 v1 bar plus m2 v2 bar by m1 plus m2. Here m1 equal to 100 grams, v1 bar is 10 I bar, m2 equal to 500 grams, v2 bar equal to 3 I bar plus 5 j bar. This you can try to simplify it to yourself now. Come on, copy down and complete the calculation part. If you want require more time, you can take a pause. So for question number 14, third option is answer. For question number 14, third option is answer. See the next question here. Question number 15. This question was also given, similar model, one of the All India entrance examinations. Two blocks of masses 10 kg and 4 kg are connected by a spring of negligible mass and placed on a frictionless horizontal surface. An impulse gives a velocity of 14 meters per second to the heavier block. In the direction of the lighter block. Velocity gained by center of mass is. So we consider the two masses m1 and m2. Here m1 is 10 kg and m2 is equal to 4 kg. And the spring, all the three together as one system. So the mass m1 is given impulse. That means it is given an impulsive force acts on m1, so that it just gains some velocity. Let v1 bar denote the velocity given to the mass m1 due to the impulse given to the mass m1. The mass m2 was initially at rest. So when we consider the two mass m1 and 2 and spring, all the three as one system, then after the impulse is given to m1, no external forces continuously act on the system during the subsequent motion. So therefore, velocity center of mass system of the two masses and the spring remains constant during the subsequent motion. Here mass of spring is assumed to be negligible or zero. So the velocity gained by center of mass just after the impulse is given equal m1 v1 bar plus m2 v2 bar by m1 plus m2. Here the v2 is 0. Therefore, direction of the velocity center of mass is in the direction of v1 bar. That is towards right. So magnitude of the velocity center of mass equal m1 is 10 kg here, m2 is 4 kg. The velocity gained with the first mass just after the impulse is given to it is 14 meter per second. So velocity gained by the center of mass, you get 10 meter per second. So answer is 10 meter per second towards right or in the direction of the velocity gain will be given to the first mass. But during subsequent motion, the velocity V1 and V2 will be changing, but velocity center of mass remains constant during subsequent motion. So for question number 15, third option is answer. See the next question here. Question number 16. This I have already discussed this in the theory part. You can see the question number 16. The velocities of two particles of masses m1 and m2 relative to a stationary observer on the earth are v1 bar and v2 bar respectively. The center of mass frame, if v1 bar is not equal to v2 bar, the two particles, 4 options are given. As already discussed, if two particles move with different velocities or unequal velocities with respect to stationary observer on the earth, then in the center of mass reference frame, the two particles always appear to move in opposite directions. Therefore, for question number 16, second option is answer. Next, I am going to discuss the question number 17 here. Two particles of masses 1 gram and 2 gram are moving with velocities 10 meter per second towards east and 10 meter per second in direction 30 degrees west of north, respectively, on a horizontal plane. The magnetic velocity center of mass system of the two particles and direction are. So I take m1 is mass, m1 is for 2 grams here, m2 equal to, m1 is 1 gram and m2 equal to 2 grams. I choose a coordinate system to represent the velocities in vector form. I choose the horizontal direction towards east as positive direction of x-axis and the horizontal direction towards north as the positive direction of y-axis. The velocity of the first particle is towards east, that means direct along positive x-axis. So in vector form, the velocity v1 bar of the first particle we can write 10 meter per second into I cap, because any vector can be expressed as the product of its magnitude and unit vector in same direction. I cap is unit vector along positive x-axis, that means directed towards east. The velocity of second particle is given to 10 meter per second in the direction 30 degrees west of north. That means the velocity of second particle has a magnitude of 10 meter per second denoted by v2 bar in vector form and makes an angle of 30 degrees with north direction. 30 degrees west of north means 30 degrees with north direction if it inclined towards west. So you can resolve the velocity vector v2 bar of second particle into rectangular components along the north and west directions. For that, you have to construct a rectangle with adjacent sides along the north and west directions, such that the velocity v2 bar of second particle acts along the diagonal of the rectangle. This component velocity of second particle directed towards north, which makes 30 degrees with v2 bar, will be equal to v2 cos 30 degrees. The other component will have magnitude v2 sin 30 degrees. That means the velocity of second particle has rectangular components along west and north direction. That means along negative x-axis and positive axis. So in vector form, the velocity v2 bar of second particle, you can write v2 sin 30 degrees into minus I cap, because it is directed towards west along negative direction of x-axis, plus V2 cos 30 degrees into j cap. Velocity vector v bar in the xy plane can be written in the form vx I cap plus vy j cap. Here v2 is the magnetic velocity second particle, that is 10 meter per second. Sin 30 degrees you can take 1 by 2. And cos 30 degrees equal to root 3 by 2. So in vector form, the velocity v2 bar of the second particle can write minus 5 I cap plus pi root 3 into j cap meter per second. So the velocity of center of mass of system of the two particles is given by m1 v1 bar plus m2 v2 bar divided by m1 plus m2. Here m1 equal to 1 gram, units of mass get cancelled. So it's not compulsory to convert the masses from gram to kg because units of mass get cancelled. m1 is 1 gram here, v1 bar equal to 10 I cap meter per second. m2 is 2 grams here, v2 bar equal to minus 5 I cap plus pi root 3 j cap meter per second by m1 plus m2 1 plus 2. This you can try to simplify it yourself. If you want to copy down the solution of this problem, you can take a pause and copy down the solution of the problem. So velocity center of mass you get 10 root 3 j cap by 3 meter per second, or you get 10 by root 3 j cap meter per second. J cap is unit vector along positive axis towards north. That means the magnetic velocity of 10 center of mass is 10 root 3 meter per second. Direction of the velocity center of mass is towards north along positive axis. In case you need more time to copy this solution, you can take a pause and take your time. So for question number 17, you get the second option as the answer. So next, see the next question. Question number 18, the more easier problem. System consists of two identical particles. One particle is at rest, another particle has an acceleration A. The center of mass system has an acceleration of. So acceleration center of mass system of the two particles is given by m1 a1 bar plus m2 a2 bar by m1 plus m2. Here both the particles have same mass because they are identical particles. Acceleration of one of the particles you can take it as 0. The mass of second particle m2 is also equal to m1. Acceleration of other particle a2 bar is equal to a bar. m2 is also equal to m1. This you can try to simplify it yourself. So you get acceleration center of mass equal to a bar by 2. That means half of the acceleration of second particle. So for question number 18, third option is the answer. So I am going to discuss the next question. Question number 19. This I have discussed in one of special cases here. Two particles A and B at rest move towards each other under their mutual force of attraction. At the instant when the speed of A is V, the speed of B is to V, the speed of center of mass system. Here initial velocity of each mass is 0. So initial velocity of center of mass of system of the two particles by m1 into initial velocity of A plus m2 into initial velocity of B by m1 plus m2. M1 is the mass of A, m2 is the mass. Initial velocity of A is 0. Initial velocity of B is 0 because both are initial at rest. So initial velocity center of mass 0. And no external force act on system. The velocity of center of mass of system remains constant, both in magnitude and direction. So final velocity center of mass later instant is same as the initial velocity center of mass at the earlier instant. When the two particles move only due to the internal force. So initially velocity of center of mass of system is 0, therefore final velocity center of mass is 0. So for 19th question, first option is the answer. See the question number 20. This question number 20 is also based on the same concept. When no external force act on system, velocity center of mass system remains constant both in magnitude and direction. The resultant of all the external forces acting on system is 0, or no net external force acts on system. The velocity center of mass system remains constant. So final velocity center of mass at later instant will be same as the initial velocity center of mass at the earlier instant. The initial velocity center of mass at the earlier instant is 0.5 meter per second. So final velocity center of mass at later instant will also be 0.5 meter per second. So for the question number 20, second option is the answer. Next is see the next question. Question number 21. This problem comes under one of the special cases which I have discussed earlier. Here two particles A and B of mass of 2 kg and 3 kg at rest are separated by 10 meters. They move toward each other under mutual force of attraction. The distance of point from the initial position of where they meet is, as I told you, if the 2 point masses are initially at rest, and if they start moving towards each other only under the mutual force of attraction, and if no external force acts on the system, then the two particles collide or meet each other at the position of their center of mass. You have to find the position of the center of mass of system of the two particles at which the two particles meet each other. Choose the position of, let D1 be the initial distance of M1 from the center of mass of the two particles, and D2 is the initial distance of M2 from center of mass of the two particles. The two particles are initially at rest, and they start moving toward each other only due to the mutual internal forces. And these internal forces cannot change the position of center of mass system. So center of mass system will be continues to be at rest. So initial separation between them is 10 meters. So ratio of the distances of two masses from the center of mass will be equal to inverse ratio of their masses. And D1 plus D2 is the initial separation between them, we denote it by R. That is 10 meters. So D1 you get, if you solve these two equations, D1 you get M2R by M1 plus M2. Here M2 equal to 3 kg, M1 is equal to 2 kg. R is the initial separation between them, which is equal to 10 meters. So you get 6 meters as the answer. So for question number 21, third option is the answer. Next, see the question number 22. A shell projected from a level ground has a range R if it did not explode. At the highest point, the shell explodes into two fragments, having masses in the ratio 1:3, with each fragment moving horizontally immediately after the explosion. The lighter fragment falls at distance R from the point of projection, behind the point of projection. The distance at which the other fragment falls on the point of projection is. Here the shell explodes due to the internal forces within the shell. The internal forces play no role in the motion of center of mass. Therefore, the path followed with center of mass of system, that means shell, will not be affected by the explosion, because the explosion is caused by internal forces which play no role in the motion of center of mass system. The path followed by center of mass system is governed only by the external force acting on system. Here the external force on the system is the same, is the force of gravity, whether the body explodes or does not explode. M is the total mass of the system. The external force on the system is equal to mg, has magnitude mg. That means the external force on the shell or system is the same whether the body explodes or doesn't explode. Therefore, acceleration center of mass of system will be equal to the acceleration due to gravity, irrespective of whether the body explodes or does not explode. Therefore, the center of mass system of the two parts continues to move along the same parabolic path along which the unexploded body would have traveled. If the body does not explode, if the shell does not explode, then it moves in a parabolic path under influence of gravity and covers a horizontal range R. I choose the horizontal direction passing through this point of projection as x-axis. Even if the body explodes due to the internal forces, the different parts may move in different directions, but center of mass of all the parts continues to travel along the same parabolic path along which the unexploded body would have traveled, and reaches center of mass when both the parts of the shell, when both the part into which the shell explodes have reached the ground, center of mass will reach the same point A on the ground at which the unexploded body would have landed. So here I choose the point of projection of the projectile as origin, horizontal direction passing through point of projection of the x-axis. The first part falls at a distance r from the point of projection behind the point of projection. That means falls on the negative x-axis. So masses of the two fragments M1 and M2 are in the ratio 1:3. So I can take M2 is 3 times M1. 6 coordinate center of mass system of the two bodies. When both the bodies parts have just landed onto the ground, you can write M1 x1 plus M2 x2 by M1 plus M2. When both the parts have reached the ground, x coordinate center of mass you can write as equal to r. X1 can be written minus r because the first part falls behind the point of projection at same distance r on negative x-axis. M2 you can write 3 times M1. Or to find x2 here, come on, copy down this working and try to complete the simplification part yourself. Solve for x2, simplify it yourself. You're supposed to get it as x2 as 5r by 3. In case you need more time to copy this, you can take a pause and copy down. So for question number 22, second option is the answer. So next I'm going to discuss the next question. See the question number 23. This I have discussed actually in one of the special cases. This problem comes under one of the special cases I discussed previously. See, two lead balls of masses m and 5m and radii r and 2r are separated by 12r between their centers or initially at rest. They attract each other by gravitational force. The distance covered by small sphere before they touch each other is. So here the mass of the first sphere m1 equal to m. The mass of second sphere m2 equal to 5m. Radius of first sphere denoted by r1 equal to r. Radius of second sphere denoted by r2 equal to r. The initial separation between the two spheres are denoted by d earlier, that is equal to 12r. As I discussed in one of special cases earlier, if you remember the result, you can straight away use the result. First, I solve the problem by using the conclusion which I have already discussed. Next, I also solve it by the principle also, in case you. So, distance moved by the first sphere before they collide with each other. You can write m2 by m1 plus m2 into d minus r1 plus r2. In case remember the conclusion which I have discussed in one of special cases, you can directly use the conclusion like this. M2 is 5m, m1 equal to m, d equal to 12r, r1 plus r2 will be r plus 2r or 3r. This you can simplify further. You get 7.5r as the answer. In case you need time to copy this, you can take a pause. So for question number 23, second option is the answer. I would like next discuss the alternate method for this question number 23. So I am discussing the alternate method for the same question number 23. The mass, let O be the initial center of the first sphere. To take it as origin coordinate system with mass m. The initial position of center of second sphere is a distance 12 into Kepler from center of first sphere. Let S1 be the distance moved by center of first sphere and S2 is the distance moved by center of second sphere before the two spheres collide with each other. At the instant the two spheres collide with each other, distance between their centers is equal to sum of the radii of the two spheres, which is equal to r plus 2r or 3r. The two spheres are initially at rest. So initial mass of each sphere is 0. Initial mass center of mass system of the two spheres is also 0. And no external force are acting on system, therefore velocity center of mass system remains constant. So initial mass center of mass system of the two spheres is 0 because they are initially at rest. So final velocity center of mass is also 0 because velocity center of mass remains constant. Center of mass system is at rest. Therefore distance of center of mass from the origin O remains same in both cases. I choose the line join the centers of the two spheres at x-axis. Initial position of the center of first sphere at the origin. Because center of mass system is at rest. Distance of center of mass from the origin in second case, same as distance center of mass from the origin in first case. Distance center of mass is from the origin in the first case, you can write m1 x1 plus m2 x2 by m1 plus m2. Distance of center of mass from the origin in second case, you can write m1 into x1 dash plus m2 into x2 dash by m1 plus m2. You can cancel m1 plus m2 here. So here x1 is the initial distance of m1 from origin, that is 0. x2 is the initial distance center of second sphere from origin, that is 12r. x1 dash is the new distance center of first sphere from origin, that is s1, which you have to find. x2 dash is the new distance center of second sphere from origin, that is equal to s1 plus r1 plus r2. r1 plus r2 is equal to 3r, or s1 plus 3r. So come on, substitute all these values and simplify it yourself. M1 equal to M. X1 is 0. M2 is 5M. X2 equal 12R. X1 dash is S1. I written interchanged here. M2 is 5M. X2 dash is S1 plus 3R. Simplify this, and you can see from the figure that S1 plus R1 plus R2 plus S2 is 12R. From here you get 5 into 12R equal to 6S1 plus 15R. From the figure you can observe that S1 plus R1 plus R2 plus S2 is 12R. The next step is substitute R1 plus R2 equal to 3R and solve this equation. This you call it as first equation. This is second equation. Solve these two equations to find S1. Or even if you solve the first equation, you get S1. Don't require the second equation actually. You can solve this first equation to find S1. You get S1 equals 7.5R. Same answer you get.